Alright guys, so here we go, nuclear chemistry. Alright, so our first section, so this is in chapter 4, chapter 5 of the book, if you guys ever pull it out and look at it. Alright, so looking at the nucleus and looking at how we determine radioactive nuclear radiation and that kind of stuff. Alright, so when was radioactive decay discovered? Well, the first person who discovered it, the way they did it was they simply took a piece of uranium, right, put it on a photo plate, back when they had to actually develop photos, and had it on paper, right, so a piece of uranium here, and he had it wrapped on a film, and then when he pulled out that slide and then developed it, the negative had a nice big white spot on the picture, right, where the uranium had been. So he knew some sort of energy was coming out of that uranium ore, all right, and so discovered that that was where radioactive decay was starting to happen. The guy who came up with this, who did this experiment, his name was Antoine Henry Becquerel, and so there's a picture of what he looked like. And he then, this is when he discovered it. It was in 1896. Okay, so just explains what happened there. He saw that photographic plate develop, bright spots when it was exposed to the uranium metals, right? And so he figured that some sort of radiation or particle was being emitted by that rock. All right, so types of reactions we're going to look at. We got radioactive decay, all right, where the nucleus of a element breaks apart, giving off energetic particles. We're going to talk more about that later. And then you've got nuclear bombardment, where you shoot a high energy particle at a nucleus of another atom, and then you see what happens, right? And so this leads into other things like military purposes, like nuclear weapons and that sort of thing. Alright, so normally when you have some sort of decay, you end up with a element that's being given off. Right, so here we got SY, which is just a symbol for an element. Usually it's helium, right? The mass number, so if it was helium, the mass would be 4. The atomic number, right, which is the Z there, that's normally 2 if it's helium. So, but it can be different depending on what we're having break off of that nucleus of the atom. Okay, so here are the different ones that we see, right? You've got alpha particles, right? This is normally a helium, which consists of 2 protons, 2 neutrons, all right, and it's escaping from that nucleus. You got beta particles, where you get an electron that escapes, and then you got gamma radiation, which is what that little symbol there stands for, where you've got some sort of high electromagnetic radiation coming at you, all right? Alright, so how far do different types of radiations go? Well, you can see here you've got alpha, which is that A looking symbol there, right? It only goes through, like, it can be stopped by paper, metal foil, thin clothing, right? So this stuff, you're usually good. This kind of radiation you would get from, like, the sun, to get a sunburn, that kind of stuff, right? It can be stopped by clothes. Alright, beta radiation, normally you're going to need some sort of metal sheeting, right? So maybe some iron, things like that, maybe really dense wood or some heavy clothing. It can stop that. So it'll pass through normal clothing, but dense clothing, wool, that kind of stuff, you're good. And then gamma radiation, which is of course the most dangerous, it can pass through all those different things, flesh, metal, wood, all that clothing. And normally you need to stop it with either a thick wall of concrete or a thick wall of lead. And so that's what most like bomb shelters have to have in order to stop that kind of radiation. All right, so a little example here. So think of it, if alpha is kind of like this truck here, right? It doesn't go very far, but it does, but totals whatever it hits, right? So like if it hits your skin, it's going to do damage, right? So that's why you can get sunburn, get cancer from that, because that radiation coming from the sun does a lot of damage. And then you got beta, which is like the car. It doesn't do quite as much damage, but it does go further into the body, right? And so it can actually affect some of that, your chromosomes and DNA and things like that. And then you got the last one there, which is the motorcycle, which is like gamma radiation, right? It doesn't do a whole lot of damage, but it goes really fast. So when it does hit something, it really does knock it down, knock it out pretty quickly. So it can be definitely the most dangerous, just because of how much it passes through. It goes through your entire body. Alright, so question here. Which component of radioactivity would be stopped by a single page? Which 2 components would be stopped by this book if you were holding a book, right? or which component would pass through almost undiminished through both the single page and the entire book? Well, if you don't know, go back, look at the notes again right there, and you should figure it out. Okay, so here are the different kinds of radioactive decay we're going to look at, right? You've got alpha particle emission, beta emission, positron emission, electron capture, and gamma emission. All right, so we're going to take a look at those right here. All right, so alpha particle. All right, well, when that happens, right, you've got your nucleus, and normally what happens is it's usually uranium, plutonium, something like that. This helium particle breaks off, and that causes the nucleus to get smaller for the uranium, plutonium, and then this helium will break off. And what it does is it'll hit another uranium, and it kind of will cause a chain reaction if they're really close together. If not, it just works its way out into the system, and and it can affect things that are around it. All right, so here's an example. All right, I've got uranium-238. That's its mass. Its atomic number is 92. Well, then when helium breaks off, it loses 2 protons, and then it loses 2 neutrons. So altogether, it loses 4, right? So that's where the helium gets the 4, and it loses the 2 protons. So now it's no longer uranium, it becomes thallium. All right, and so, which is not as radioactive as uranium. Still radioactive, but not as much. All right, so what would happen if I had some plutonium-239, right? And it loses an alpha particle, which is a helium nucleus. So what would that reaction look like? All right, so take a second, write it out, think about it. So you should end up with, remember, plutonium losing 4 altogether, so it should end up becoming 235, and then you're going to have that helium gaining 2, right? And so the atomic number is going to go down on the plutonium. All right, beta emission, okay? This is where a neutron splits into a proton and an electron, which is spit out as a beta particle. So basically, one of the protons in the nucleus, here you've got carbon-14, it separates, you get a neutron, so the 14 doesn't change, right? And you get a proton, which is formed, so the atomic number goes up, and then an electron escapes. So you can see here, carbon-14 becomes nitrogen-14. And it gains a proton, but it loses the electron, and that's what's being emitted. That's the radiation that's coming off of there.